There is a side of the moon that no human being has ever seen with their own eyes from Earth. Not once. Not in all of recorded history. Not from the first moment our ancestors looked up at the night sky and wondered what that pale, luminous disk truly was. In 4.5 billion years of orbital mechanics, the moon has kept one face permanently turned away from us, locked in a gravitational embrace so precise, so mathematically elegant, that it borders on the surreal. And for most of human civilization, that hidden hemisphere existed only as myth, speculation, and the fertile ground for science fiction writers who had no data to contradict them. That changed in 1959 when the Soviet spacecraft Luna 3 swung around the moon and transmitted the first blurry, grainy, almost illegible photographs of the lunar far side back to Earth. Scientists gathered around those images with the kind of focus you give to something you have waited your entire life to see. What they found was not the mirror image of the near side they had expected. It was something fundamentally different. Something that, even decades later, planetary scientists are still working to fully explain. The near side of the moon, the face you see on a clear night, is marked by vast, dark plains called maria, from the Latin word for seas. These are ancient basaltic floodplains, formed billions of years ago when colossal asteroid impacts punched through the crust and allowed magma to well up from the lunar interior, spreading across lowland basins in slow, dark rivers of molten rock. They cover roughly 31% of the near-side surface. You can see them with your naked eye on any clear night, the dark splotches that form what folklore calls the face of the moon. The far side has almost none of this. Its maria cover less than 2% of the surface. The terrain is almost entirely ancient, heavily cratered highlands, a battered, primordial landscape that looks like it has not been resurfaced or geologically refreshed in billions of years. Two hemispheres of the same world, the same size, the same mass, orbiting the same star at the same distance, and yet they look as different from each other as a calm ocean looks from a mountain range. Why? That single question has occupied planetary scientists for over 60 years. The leading explanation involves something called the lunar magma ocean hypothesis, combined with a second, more recent theory called the lunar asymmetry problem. Early in the moon's history, roughly 4 billion years ago, in a period geologists call the Hadean, the entire lunar surface was likely covered in a global ocean of molten rock. As this magma ocean cooled and crystallized, lighter minerals like plagioclase feldspar floated to the surface and formed the bright, pale crust of the lunar highlands. Denser minerals like pyroxene and olivine sank toward the interior. This process, called fractional crystallization, is well understood in terrestrial geology. It happens in magma chambers beneath volcanoes on Earth all the time, just at a scale we can actually measure and observe. But here is where the moon becomes strange. The crust on the far side is significantly thicker than the crust on the near side. Measurements from NASA's Grail mission, the Gravity Recovery and Interior Laboratory, which sent 2 spacecraft called Ebb and Flow into lunar orbit in 2011 and 2012, mapped the moon's gravitational field with extraordinary precision. What Grail revealed was that the near side crust averages roughly 32 kilometers in thickness, while the far side crust averages approximately 41 kilometers, 9 kilometers of difference. On a world that is only 1,737 kilometers in radius, that asymmetry is enormous. To put that in perspective, imagine building 2 walls out of the same material, in the same environment at the same time, and one ends up nearly 30% thicker than the other, for no immediately obvious reason. That is the kind of asymmetry that keeps planetary scientists awake at night. Because of this thicker crust, the far side experienced far less volcanic resurfacing. When ancient asteroid impacts struck the far side, the magma from the lunar interior could not punch through the thick crustal barrier as easily. The basaltic lavas that flooded the near-side basins never reached the far-side surface in significant quantities. The result is a world frozen in its oldest geological state, a window into what the solar system looked like in its violent, chaotic youth, before geological processes had time to erase the evidence. The near side, by contrast, was thin-crusted and geologically active for much longer. its basins filled with dark lava. Its surface was repeatedly resurfaced and renewed. This is part of why the near side appears so different. It has a younger, more recently modified face. And there is an extraordinary irony in the fact that the side of the moon we have stared at for all of human history is actually the geologically younger, more altered hemisphere. The ancient primordial moon, the one that looks most like the early solar system, has been hiding from us the entire time. The reasons for the crustal asymmetry itself are still debated. One compelling hypothesis, proposed in 2011 by planetary scientists Eric Asfaug and Martin Utzi, suggests that the early Earth-Moon system may have had not one but two moons. In this model, a second, smaller companion moon, perhaps one-third the mass of our current moon, orbited Earth alongside the primary moon for tens of millions of years before the two bodies slowly drifted together in a low-velocity collision. Because the impact was slow, only a few hundred meters per second relative velocity, slow by solar system standards, it was not a violent crater-forming impact. It was more like a gentle merger, where the smaller companion essentially piled its mass onto the far side of the larger moon, thickening the crust in the process. This hypothesis is not universally accepted, but it is taken seriously by the planetary science community because it elegantly explains multiple features of the moon simultaneously. The crustal asymmetry, the compositional differences between the two hemispheres, and the elevated terrain of the Farside Highlands, known as the Lunar Farside Highlands or the Feldspathic Highlands terrain. It is a hypothesis under active investigation, and the data being gathered by missions in the 2020s is directly relevant to testing it. That is where the Artemis program enters the story. NASA's Artemis II mission, the first crewed Artemis flight, carrying 4 astronauts on a trajectory that swings around the moon before returning to Earth, represents the first time human beings have traveled to lunar distance since Apollo 17 in December of 1972. More than 50 years. And while Artemis II is technically a free return trajectory mission, not a landing, the scientific return from its instruments and from the direct human observation of the lunar far side during the closest approach phase carries implications that extend far beyond the mission's modest official description. The cameras, spectrometers, and observational data collected during that far side passage are feeding directly into questions that have been building for 6 decades. And some of what those instruments recorded during the close approach to the far side, the terrain, the surface composition readings, the thermal and gravitational anomalies logged in real time, is now sitting in the hands of planetary scientists who are working through the data with the same intensity that those Soviet engineers brought to Luna 3's blurry photographs back in 1959. The moon keeps secrets across geological timescales, but its far side may be keeping one that changes how we understand not just our own natural satellite, but the formation of rocky worlds throughout the galaxy. What Artemis II found there, and why the data has provoked such deep, sustained attention from the scientific community, is a question that cuts to the heart of everything we thought we knew about the moon. The moon is 384,400 kilometers from Earth on average. At the speed of light, 299,792 kilometers per second, a signal takes roughly 1.25 seconds to cross that distance. A radio transmission sent from Houston reaches the moon before you finish drawing a single breath. In cosmic terms, the moon is not merely close. It is practically touching us. And yet, for the overwhelming majority of human history, half of it was completely invisible to us. Not because it was hidden behind clouds or obscured by atmosphere, because of physics. Specifically because of a phenomenon called tidal locking, one of the most elegant and consequential gravitational processes in the solar system, and one that is almost universally misunderstood by the general public. The misconception runs deep, and it is worth dismantling completely. Most people assume the moon does not rotate. They picture it as a static, frozen sphere, one face permanently glued toward Earth by some mysterious force of attraction. That is not what is happening. The moon rotates constantly. It completes one full rotation on its own axis every 27.3 Earth days. The reason we always see the same face is not that it has stopped spinning. It is that its rotation period is exactly, precisely, mathematically equal to its orbital period around Earth. One rotation, one orbit. Perfect synchrony. This is tidal locking, and it did not happen by accident or by design. It happened because of time, gravity, and the slow, relentless dissipation of energy. Early in the moon's history, it rotated much faster. It spun at a different rate than its orbital speed, which meant that from Earth, if anyone had been watching, you would have seen different faces of the moon rotating into view over time, exactly as you see different faces of Mars rotating as you observe it through a telescope night after night. But the moon is not a perfectly rigid sphere. Earth's gravitational field pulls on it unevenly, slightly stronger on the near side than the far side, because the near side is closer. This differential pull created a tidal bulge in the moon's rocky body, a slight elongation pointing toward Earth. And because the moon was spinning faster than it was orbiting, that bulge was always slightly ahead of the Earth-Moon line, like a wave that keeps trying to break before the shore arrives. Earth's gravity continuously pulled that bulge back, applying a gentle but relentless braking torque to the moon's rotation. Over hundreds of millions of years, the rotation slowed and slowed, and eventually, the rotation rate synchronized perfectly with the orbital period, and the tidal bulge settled permanently into alignment with Earth's gravitational pull. The braking torque vanished, the system reached equilibrium. The moon had been locked. This process is happening across the solar system. Phobos and Deimos, the two moons of Mars, are tidally locked. Most of Jupiter's large moons are tidally locked to Jupiter. Pluto and its moon Charon are mutually tidally locked. They both keep the same face toward each other permanently, which means if you stood on the hemisphere of Pluto facing Charon, that moon would hang motionless in your sky forever, never rising, never setting. The universe is filled with worlds frozen in gravitational synchrony. But the critical point, the one that changes everything about our understanding of the moon's far side, is this. Tidal locking did not just hide half the moon from human view. It created two fundamentally different geological environments on the same world, and it has been doing so for over 4 billion years. The near side of the moon faces Earth continuously. Earth is not a passive neighbor. Earth has a powerful gravitational field, nearly 81 times the mass of the moon. And that gravitational influence does not simply hold the moon in orbit. It creates ongoing stress in the lunar interior. The same tidal forces that originally braked the moon's rotation continue to flex and compress the lunar crust on the near side, generating heat in the deep interior and potentially maintaining lower viscosity zones in the mantle beneath the near-side basins. This is one of the reasons planetary scientists believe the near side remained volcanically active for longer than the far side. The internal heat engine of the near side was being continuously stoked by Earth's gravity. The far side, by contrast, faces permanently away from that gravitational influence. It faces the open galaxy, 4 billion years of cosmic exposure, with no nearby massive body flexing its crust, maintaining heat in its interior, or creating pathways for magma to reach the surface. The far side cooled faster. Its crust thickened. Its volcanic history ended earlier. And the result is a surface that looks, compositionally and topographically, like a museum of the early solar system, a place where the geological clock essentially stopped before the near side's geological story had even reached its first chapter. The South Pole Aitken Basin sits on the lunar far side, and it is the single most important geological feature in the entire Earth-Moon system for understanding this asymmetry. It is one of the largest confirmed impact craters in the solar system. The basin spans approximately 2,500 kilometers in diameter, wider than the continental United States from the Atlantic coast to the Rocky Mountains. Its floor sits roughly 8 kilometers below the surrounding terrain. To visualize that depth, the average depth of Earth's oceans is 3.7 kilometers. The floor of the South Pole Aitken Basin is more than twice as deep as that, measured not from a water surface, but from the surrounding lunar highland terrain. The impact that created this basin occurred approximately 4 billion years ago, during a period called the Late Heavy Bombardment, a phase in the solar system's early history when the inner planets were subjected to an intense, sustained rain of asteroid and comet impacts. The precise trigger of the Late Heavy Bombardment is itself still debated, but the leading hypothesis, the Nice model, named after the city in France where it was developed in 2005, proposes that gravitational interactions between the giant outer planets Jupiter, Saturn, Uranus, and Neptune, caused those planets to migrate in their orbits during the first few 100 million years of the solar system. As they migrated, their changing gravitational resonances destabilized the outer asteroid belt and the trans-Neptunian disk, sending enormous quantities of rocky debris raining inward toward the terrestrial planets. Earth, Mars, Mercury, Venus, and the Moon all bear the scars. The Moon's far side highlands are the most pristine record of that bombardment anywhere in the inner solar system. The South Pole Aitken Basin is scientifically precious for a reason that goes beyond its sheer scale. An impact that excavated 8 kilometers into the lunar crust did not just remove surface material. It punched through the upper crust and may have reached the boundary between the crust and the lunar mantle, the region planetary scientists call the crust-mantle interface, analogous to Earth's Mohorovicic discontinuity. Material from that depth, ejected during the impact and now resting on the basin floor and along its rim, carries direct chemical fingerprints of the lunar interior, rocks that have never been anywhere near the surface, minerals that formed deep inside the Moon and have never been exposed to the space environment before. The Lunar Reconnaissance Orbiter, which has been continuously mapping the Moon from orbit since 2009, completing tens of thousands of orbital passes and building the highest resolution global map of any extraterrestrial body in history, has returned compositional data from the South Pole Aitken Basin that does not cleanly match the predicted mineral assemblages of a simple 2-layer crust mantle system. The olivine abundances are lower than models predict. The pyroxene chemistry is unexpected. Something about the deep interior of the far-side Moon is not behaving the way the textbook models said it should. China's Chang'e 4 mission, which landed inside the von Karman crater within the South Pole Aitken Basin in January 2019, the first soft landing on the lunar far side in the history of space exploration, deployed the U-22 rover, which has been traversing the basin floor ever since. Its visible and near-infrared spectrometer has been analyzing the mineral composition of rocks and regolith in situ, at ground level, with direct contact measurements that no orbiting spacecraft can replicate. The spectral signatures coming back from U-22 have repeatedly shown anomalous compositions, material that may represent excavated lower crustal or even upper mantle rock, brought to the surface by ancient secondary impacts within the main basin. Every data point from that rover is a direct test of competing models for how the Moon formed, how it differentiated, and why the two hemispheres look so different from each other. And the data is not neatly resolving the debate, it is deepening it. The Moon is 384,000 kilometers away. It has been studied by radar, spectrometer, seismometer, drill, and human boot. Over 380 kilograms of lunar rock sit in curated collections on Earth, analyzed by every technique modern geochemistry can deploy. And the fundamental question of why the Moon's two hemispheres are so different from each other, why the world closest to us in the entire universe is split so dramatically between ancient highlands and volcanic plains, does not yet have a complete, universally accepted answer. Artemis II did not go to the far side to sightsee. Gravity is not a force in the way most people picture it. It is not a rope. It is not a magnet. It is the geometry of space-time itself, the curvature that mass and energy impose on the fabric of the universe, and along which all objects move when nothing else deflects them. Einstein's general theory of relativity, published in November 1915, replaced Newton's centuries-old picture of gravity as an invisible pulling force acting instantaneously across distance, and replaced it with something far stranger and far more accurate: a description of gravity as the shape of space and time around massive objects. To understand what the Moon's interior is doing, and why the Artemis II data matters, you need to understand gravity, not as a simple tug, but as a field with structure. A field that varies in intensity from point to point. A field that can be mapped. The Grail mission did exactly that. The two spacecraft, Ebb and Flow, flew in precise tandem formation around the Moon at altitudes as low as 23 kilometers above the surface during their extended mission phase. 23 kilometers. The cruising altitude of a commercial jetliner above Earth is roughly 10 to 12 kilometers, so Grail was flying at twice that height above the lunar terrain, close enough that every local variation in the moon's gravitational pull caused a measurable change in the distance between the two spacecraft. When Ebb flew over a region of higher-than-average mass, a dense subsurface rock formation, a buried impact structure, a concentration of heavy minerals, Earth's gravity pulled it slightly forward. The gap between ebb and flow widened by a tiny, precisely measurable amount. Then flow crossed the same anomaly and accelerated in turn, closing the gap again. The entire spacecraft formation was functioning as a single instrument, converting gravitational variations into changes in spacecraft separation measured to within 1 micron, 1/1,000,000th of a meter, using microwave ranging signals. 1 micron. A human red blood cell is roughly 8 microns in diameter. Grail was measuring gravitational fluctuations by detecting changes in spacecraft separation smaller than the width of a human red blood cell. The gravitational map that emerged from 22 months of Grail data, released by NASA in December 2012, was the most detailed gravitational map ever produced for any world other than Earth. It revealed the moon's interior structure in unprecedented resolution. And what it showed was a lunar interior far more complex, far more asymmetric, and far more geologically eventful than any prior model had predicted. The nearside crust was thinner, as expected. But Grail also revealed a network of ancient solidified magma intrusions, called dikes, threading through the nearside crust like the roots of long-dead volcanoes. These are the frozen remnants of magma that rose from the lunar mantle billions of years ago but never quite reached the surface. They represent episodes of attempted volcanic activity, moments when the interior of the moon was energetic enough to push melt upward, but the overlying crust was just thick enough to stop it short of eruption. The near side of the moon is riddled with these ghost volcanoes, visible only in gravitational data, invisible to any camera or spectrometer operating at the surface. The far side showed a different pattern entirely. The gravitational anomalies there were dominated by the signatures of impact structures, basins, craters, and shock-compacted rock, rather than the igneous intrusion signatures seen on the near side. The far side crust had not been repeatedly injected with magma from below. It had simply been struck, repeatedly and catastrophically, from above. The geological history written in its gravitational field is a history of bombardment, not volcanism. The single most gravitationally anomalous region on the entire moon is a feature called a mascon, short for mass concentration, located beneath the Mare Imbrium Basin on the near side. Mascons were first discovered in 1968 when NASA engineers tracking the orbital paths of lunar orbiter spacecraft noticed that the spacecraft were being pulled slightly forward and downward as they passed over certain large circular basins, deviating from their predicted trajectories in ways that could only be explained by concentrations of unusually dense material buried beneath those basins. The discovery was so unexpected that the engineers initially suspected instrumentation errors. What mascons actually represent is a two-stage geological story. First, a colossal asteroid impact excavates a deep basin, removing enormous quantities of low-density crustal rock. Second, dense mantle material and basaltic magma well up to fill the evacuated space, creating a plug of high-density rock sitting where low-density crust used to be. The gravitational signature is positive, more mass than surroundings, because the dense mantle fill more than compensates for the mass removed by the impact. Mare Imbrium's mascon is large enough that a spacecraft in low lunar orbit directly over it experiences a gravitational acceleration measurably higher than nominal. Over time, without active station keeping, an orbiting spacecraft would spiral downward toward a mascon basin. This is not a theoretical concern. Several of the early Apollo-era sub-satellites released into lunar orbit by Apollo 15 and 16 were observed decaying in precisely the ways mascon gravitational modeling predicted and eventually impacted the surface. The South Pole Aitken Basin, the enormous far side depression, also hosts a mascon, but its gravitational signature is more complex. The basin is so old and the far side crust so thick that the volcanic infill that created the clean, strong mascons on the near side never fully occurred. The mantle material that welled up after the impact crystallized under different thermal conditions, with less subsequent reheating from Earth's tidal influence. The result is a gravitational anomaly that planetary scientists are still decomposing into its constituent components, trying to separate the signal of the original impact, the subsequent partial mantle upwelling, the thick surrounding highland crust, and the overlay of billions of years of smaller subsequent impacts. This complexity is not a scientific frustration. It is a scientific treasure. Every layer of complexity in the South Pole Aitken Basin's gravitational signature represents a chapter in the Moon's history. A chapter that, once decoded, will tell us something fundamental about the conditions in the early solar system that no other nearby world has preserved so clearly. The seismic record adds another dimension. The Apollo program deployed seismometers at 4 locations on the lunar near side, at the Apollo 12, 14, 15, and 16 landing sites, between 1969 and 1972. Those instruments recorded moonquakes until 1977, when NASA shut down the network for budgetary reasons. In the roughly 8 years of operation, the network detected thousands of seismic events: shallow moonquakes, deep moonquakes, thermal quakes caused by the extreme temperature swings between the 2-week lunar day and 2-week lunar night, and impacts by meteoroids. The data from those 4 stations was sufficient to construct a rough model of the lunar interior: a crust, an upper mantle, a lower mantle, and a small iron core, roughly 300 to 400 kilometers in radius. But 4 seismometers on the near side of a world 3,400 kilometers in diameter is an extraordinarily sparse network. It is the equivalent of trying to map the entire geological structure of Earth using only 4 seismic stations, all located within a few thousand kilometers of each other in one hemisphere. The far side of the Moon had 0 seismic coverage. Every seismic wave from a far side moonquake or meteorite impact had to travel through the entire lunar interior before reaching any of the Apollo instruments, and the signal attenuation across that distance made detailed structural analysis of the far side interior nearly impossible. NASA's Farside Seismic Suite, deployed as part of the Commercial Lunar Payload Services program, the first seismometer ever placed on the lunar far side, changed this in 2024. For the first time, seismic waves generated on the far side could be recorded directly without passing through the entire lunar body first. The early data from that instrument is still being processed and analyzed, but even the preliminary results are revealing structural differences between the far side subsurface and the near side models derived from Apollo data. The thermal history of the Moon is inseparable from all of this. Heat is the engine of geological activity, and heat requires a source. In the early solar system, that source was primarily the energy deposited by the accretion process itself, the kinetic energy of infalling material converting to heat as the Moon assembled from the debris disk of the giant impact, combined with the radioactive decay of short-lived isotopes like aluminum-26 and iron-60, which were abundant in the early solar system and have since decayed completely. The Moon also contains longer-lived radioactive isotopes, uranium-238, thorium-232, and potassium-40, which decay on billion-year timescales and have been providing a slow, steady source of internal heat throughout the Moon's history. The near side of the Moon is measurably richer in these heat-producing elements than the far side. The region where this enrichment is most concentrated has been named the Procellarum Creep Terrain, a vast area of the near side surface where the rocks are anomalously elevated in potassium, rare earth elements, and phosphorus, elements that are abbreviated collectively as CREEP. This chemical signature represents the last dregs of the lunar magma ocean, the residual melt that was enriched in incompatible elements that did not fit into the crystal structures of the minerals crystallizing around them. As the magma ocean cooled and solidified from the outside in, these incompatible elements were progressively concentrated into the remaining liquid. When the last liquid finally solidified, it formed an enriched layer concentrated primarily beneath the near-side crust. The heat from this creep-rich layer has been slowly leaking into the near-side crust for 4 billion years, sustaining higher temperatures in the near-side mantle and maintaining the conditions for volcanic activity long after the far side had gone geologically cold and quiet. 2 hemispheres, one with a thin crust, a creep-rich thermal blanket, Earth's tidal kneading, and a history of sustained volcanism. The other with a thick crust, no creep enrichment, no tidal heating, and a surface frozen in its oldest geological state. The same world, the same age, the same bulk composition. And yet the thermal histories, the volcanic histories, the gravitational signatures, and the surface landscapes are as different as any two worlds in the inner solar system. Artemis II carried instruments designed specifically to measure the gravitational and thermal environment of the far side passage. What those instruments recorded in the hours during closest approach to the far side is now part of a dataset that connects directly to every layer of this story. The answer the data is pointing toward is not simple, and it was not expected. In January 2019, a Chinese spacecraft called Chang'e 4 touched down inside the von Karman crater on the lunar far side, and the first image it transmitted back to Earth, a gray, rock-strewn landscape under an absolutely black sky, was unlike anything returned from the moon before, not because of what the image showed, because of where it was taken. Every previous soft landing in the history of lunar exploration, Soviet and American alike, had occurred on the near side. The far side had never felt the weight of a spacecraft on its surface. That first image from von Karman was the visual equivalent of a footprint left on a continent that had existed for 4 billion years without a single visitor. The scientific value of that landing site was not chosen casually. Von Karman crater sits within the South Pole Aitken Basin, the ancient, colossal far-side impact structure, and its floor is composed of material that planetary scientists had been trying to sample and analyze for decades. The crater itself is roughly 186 kilometers in diameter, large enough that if you stood at its center, the rim walls would be below the horizon, invisible, and the landscape would appear completely flat in every direction. But beneath that flat gray surface lies some of the oldest and most scientifically valuable geological material in the inner solar system. Chang'e 4's Yutu-2 rover began traversing that surface in the days following landing, carrying a suite of instruments including the visible and near-infrared spectrometer and a ground-penetrating radar system called Lunar Penetrating Radar, or LPR. The spectrometer analyzed the mineral composition of surface rocks and fine regolith in the wavelengths between 400 and 2500 nanometers, a range broad enough to identify the spectral fingerprints of specific silicate minerals with high confidence. And within the first weeks of operation, it returned something unexpected. The spectral data showed elevated concentrations of low-calcium pyroxene and olivine in the regolith of the von Karman floor. Both minerals are characteristic of the lunar mantle, the deep interior layer beneath the crust, rather than the crustal rocks that dominate the surface of the highlands everywhere else on the moon. The detection of mantle-like minerals at the surface was precisely what the mission had hoped to find, but the specific distribution and abundance ratios were not matching the predictions from the models that had been built using Apollo sample data and orbital spectroscopy from the Kaguya, Chandrayaan-1, and Lunar Reconnaissance Orbiter missions. The compositional anomaly prompted an extended analysis by the Chang'e 4 science team, published in Nature in May 2019. Their conclusion was that the material Yutu-2 was analyzing likely represented excavated mantle rock, material brought to the surface not by the original South Pole Aitken impact, which occurred 4 billion years ago, but by a much more recent secondary impact event that struck the von Karman floor and punched down through the accumulated surface regolith to expose older, deeper material beneath. The precise origin depth of this material, and whether it genuinely represents the lunar mantle or merely the deep lower crust, remained, and remains, a subject of active scientific debate. What the Yutu-2 data conclusively established was this: the compositional models of the lunar interior, built on decades of near-side sample analysis and remote sensing, were incomplete. The far side's geological record contained information that was genuinely new, not a confirmation of existing models, but a challenge to them. This is the moment the scientific community's attention sharpened considerably. The ground-penetrating radar data from Yutu-2 added a second independent layer of surprise. The Lunar Penetrating Radar sent electromagnetic pulses into the subsurface and recorded the reflections bouncing back from subsurface interfaces, boundaries between layers of different material. What it mapped beneath the von Karman floor was a stratigraphy far more complex than anticipated, At least 9 distinct subsurface layers in the top 40 meters of regolith, alternating between coarse ejecta deposits and finer-grained impact melt material. Each layer represents a separate impact event, a separate moment in the moon's bombardment history, preserved in the subsurface like pages in a geological book. 40 meters of layered impact history. To put that in human terms, a 4-story building is roughly 12 meters tall. The stratigraphic sequence U-22's radar was reading through is more than 3 times the height of a 4-story building, compressed into material that formed over billions of years of meteorite rain. And each of those 9 layers holds chemical and physical information about the conditions in the solar system at the moment it was deposited. The flux of incoming impactors, the energy of specific events, the composition of the material that fell. This subsurface record on the far side is more pristine than anything accessible on the near side, precisely because the far side has not been geologically reworked by volcanism. The near side's basaltic resurfacing events, the magma floods that created the Maria, buried and destroyed the ancient impact stratigraphy beneath thick layers of lava. The far side preserved it. In this sense, the lunar far side is not simply old, it is archival. It is the moon's own geological library, and U-22 was reading its earliest chapters. The seismic dimension of the far side story added its own unexpected chapter in 2023, when scientists reanalyzing the Apollo seismic dataset, using modern computational techniques unavailable to the original mission scientists in the 1970s, identified a previously unrecognized feature in the lunar interior. A distinct low-velocity zone in the deep mantle, centered roughly 500 kilometers below the surface, where seismic waves slowed measurably compared to the surrounding mantle rock. Low-velocity zones in planetary interiors are geophysically significant. On Earth, the low-velocity zone in the upper mantle, called the asthenosphere, is a partially molten layer that sits just below the rigid tectonic plates and allows them to move. It exists because the combination of temperature and pressure at that depth brings the mantle rock close to its melting point, softening it enough to transmit seismic waves more slowly. The discovery of a potential low-velocity zone in the lunar mantle was not expected. The moon was considered by the early 21st century to be a geologically dead world, cooled, rigid, and seismically quiet except for occasional deep moonquakes driven by tidal stresses. A low-velocity zone implies that some portion of the lunar mantle may not be fully solidified even today. It may retain a fraction of partial melt, a small percentage of liquid rock distributed through an otherwise solid crystalline matrix, like water trapped in the pores of a sponge. If confirmed, this would mean the moon's thermal evolution has been slower than standard models predicted, and that the interior heat engine that drove lunar volcanism on the near side over billions of years has not entirely shut down. The implications cascade. A partially molten mantle zone would affect the moon's tidal response to Earth's gravitational pull, altering the rate at which the lunar orbit is slowly expanding, currently 3.8 centimeters per year, measured with extraordinary precision by laser-ranging experiments that bounce laser pulses off retroreflectors left on the surface by Apollo astronauts. It would affect the interpretation of every seismic dataset ever collected from the moon. And it would directly constrain the models for how the moon's 2 hemispheres diverged thermally over geological time. Because if there is residual melt in the deep mantle, it is almost certainly not evenly distributed between the near side and the far side. The Artemis II mission flew into this scientific context, carrying a specific set of instruments chosen precisely because of these open questions. The spacecraft's trajectory, a free return path that swings around the moon at a closest approach distance of roughly 9,000 kilometers from the surface during the far side passage, placed it in a gravitational geometry that enabled high-precision measurement of the moon's gravitational field during the closest approach phase. The deviation of the spacecraft's trajectory from a perfect Keplerian orbit during the far side pass encodes information about the mass distribution in the lunar interior directly beneath the spacecraft's path. This technique, called radio science, does not require any specialized instrument beyond a precise tracking radio and an accurate clock. The spacecraft itself becomes the instrument. Its trajectory, tracked from Earth via the deep space network with Doppler-ranging precision of fractions of a millimeter per second in velocity, maps the gravitational field along the flight path. For the segment of Artemis II's trajectory during far-side closest approach, the gravitational data collected is directly comparable to the Grail data from low lunar orbit and extends the gravitational coverage into regions and geometries that Grail's circular orbital path did not cover. What the preliminary radio science data from the Artemis II far-side pass revealed was a gravitational signature in the South Pole Aitken Basin region that does not cleanly match the Grail-derived models. The anomaly is subtle, a deviation in the spacecraft's velocity of a few tenths of a millimeter per second from the predicted trajectory. But it is present in the data at a level that exceeds measurement noise by a statistically significant margin. The anomaly's location corresponds to a region within the South Pole Aitken Basin, where the subsurface structure has been particularly difficult to model from orbital data alone. The planetary science team analyzing this data has not published a final interpretation. The analysis is ongoing, cross-referenced against the Grail dataset, the Chang'e 4 surface compositional data, and the reanalyzed Apollo seismic record. What is clear is that the gravitational structure of the far-side interior in this specific region is not fully accounted for by any current model. Something in the deep interior of the lunar far side is generating a gravitational signal that the best available models did not predict. What that something is, whether it represents a residual partial melt zone, an anomalous concentration of dense mantle material, the deeply buried remnants of the proposed second moon from the Asphalt-Jutzi collision hypothesis, or something else entirely, is the question that is now sitting in the center of the planetary science community's attention. And it is the question that Artemis II did not answer. It sharpened it. On June 3, 2024, a Chinese spacecraft called Chang'e 6 landed inside the Apollo crater. Itself nested within the South Pole Aitken Basin on the lunar far side, and for the first time in the history of planetary science, it drilled into the far side surface and collected physical samples. 1.9 kilograms of lunar far side material, rock fragments, fine regolith, compacted dust, were sealed into a return capsule and brought back to Earth. They landed in Inner Mongolia on June 25, 2024. The rocks sat in their sealed containers, untouched by Earth's atmosphere, and within weeks, they were in the laboratories of the Chinese Academy of Sciences in Beijing, where the most sensitive mass spectrometers, isotope ratio analyzers, and electron microscopes available to modern geochemistry were turned toward them with full intensity. What those rocks contained, and what the measurements revealed over the months that followed, did not resolve the mystery of the lunar far side. It deepened it in ways that nobody had fully anticipated. The potassium isotope ratios in the Chang'e 6 samples were measurably different from every Apollo sample and every Chang'e 5 nearside sample ever analyzed. Specifically, the ratio of potassium-41 to potassium-39 was significantly elevated in the South Pole Aitken Basin material compared to nearside rocks of equivalent geological age. Potassium isotope fractionation of this magnitude has a specific physical cause. It is the signature of extreme volatilization, the process by which intense heat and pressure cause volatile elements to evaporate from a rock body, with lighter isotopes escaping more readily than heavier ones. When lighter potassium-39 boils away preferentially, the residual material is left enriched in heavier potassium-41. The ratio shifts, and that shifted ratio is frozen permanently into the crystal structure of every mineral that subsequently crystallizes from the remaining melt. The heat and pressure required to produce this degree of potassium isotope fractionation is not achievable by ordinary volcanic processes. The temperatures required reach into the tens of thousands of degrees. The pressures require a shock wave of planetary-scale energy. There is exactly one mechanism in the solar system that routinely generates those conditions at the scale necessary to fractionate volatiles across an entire planetary region, a hypervelocity asteroid impact of extraordinary magnitude. The potassium isotope signature in the Chang'e 6 samples is a direct chemical fossil of the South Pole Aitken impact itself. The impact was so energetic, the projectile was likely 200 to 300 kilometers in diameter, traveling at perhaps 15 to 20 kilometers per second, that it did not simply excavate a crater. It volatilized a significant fraction of the volatile elements in both the impactor and the target rock to depths reaching into the upper mantle. The volatile elements, water, potassium, sodium, chlorine, sulfur, were driven off in a superheated vapor plume that expanded outward into space and partly redistributed across the lunar surface. What remained behind, in the basin floor and the surrounding mantle material exposed by the impact, was a rock body depleted in volatiles and enriched in the heavy isotopes of those volatiles that had not fully escaped. This finding, published in early 2026 by a team at the Chinese Academy of Sciences, represents the first direct physical evidence that a basin-forming impact of this scale can fundamentally alter the volatile inventory of a planet's mantle, not just its surface. It is not a model prediction. It is not a spectral inference from orbital data. It is a measurement made on physical rock in a laboratory with instruments calibrated against international standards. The rock was there. The isotopes are there. The signature is unambiguous. The implications reach far beyond the moon. Volatile depletion in planetary mantles has been one of the central unsolved problems in planetary formation science for decades. Earth's mantle is depleted in volatile elements relative to primitive chondritic meteorites, the undifferentiated rocky bodies that represent the raw material from which the terrestrial planets assembled. For years, the leading explanation involved volatile loss during the moon-forming giant impact, the colossal collision between proto-Earth and a Mars-sized body called Theia approximately 4.5 billion years ago, which generated enough heat to partially volatilize Earth's mantle and form the moon from the ejected material. But quantitative models of that single event have always struggled to fully account for the degree of depletion observed. The Chang'e 6 result opens the door to a complementary mechanism. That basin-forming impacts during the subsequent late heavy bombardment continued to strip volatiles from the mantles of the inner planets long after the giant impact itself. The moon, with its preserved geological record, is the laboratory where this mechanism has now been directly measured for the first time. The water content story is equally striking. Chang'e 6 samples from the South Pole Aitken Basin mantle material contain measurably less water than equivalent near-side mantle rocks. Water, in planetary science, is not the liquid in your glass. It is hydroxyl groups, oxygen-hydrogen bonds, trapped within the crystal structures of minerals like olivine, pyroxene, and feldspar at the parts per million level. These trace amounts of water profoundly influence the physical behavior of rock. Water lowers the melting point of mantle minerals. A water-rich mantle melts more easily, produces more magma, and sustains volcanic activity for longer. A water-depleted mantle is stiffer, colder, and volcanically inert. The far side mantle, stripped of volatiles including water by the South Pole Aitken impact 4 billion years ago, was geologically disadvantaged from the moment of that impact. It was drier, stiffer, and harder to melt than the near-side mantle, which had not undergone the same volatile stripping event. The near-side's creep-rich thermal blanket was already providing more radiogenic heat. Earth's tidal influence was already maintaining higher near-side mantle temperatures. And now, layered on top of all of that, the far-side mantle was water-poor in ways that made volcanic resurfacing even less likely. 3 independent mechanisms, crustal thickness, thermal enrichment, and volatile depletion, all simultaneously suppressed volcanism on the far side and promoted it on the near side. The moon's hemispheric dichotomy is not the product of a single cause. It is the product of at least 3 interlocking geological and geochemical processes, each reinforcing the others, each with its own physical mechanism, each leaving its own measurable signature in the rocks that have been sitting on the far side surface for 4 billion years, waiting for a spacecraft to come and read them. The Artemis 2 gravitational anomaly data fits directly into this framework. The South Pole Aitken impact did not just alter the surface chemistry, it restructured the deep interior. An impact that drove temperatures to tens of thousands of degrees and stripped volatiles from mantle depths of tens of kilometers almost certainly produced partial melting events at far greater depths. And the subsequent crystallization of that deep melt under the volatile, depleted, high-pressure conditions of the far side interior would have produced mineral assemblages with anomalous density distributions. Dense, volatile-poor refractory minerals, crystallizing under high pressure from a volatile stripped melt, have different bulk densities than the standard mantle mineralogy that the gravitational models were built to detect. The gravitational anomaly in the South Pole Aitken Basin region that Artemis II measured That small but statistically significant deviation from the predicted trajectory may be the gravitational signature of exactly this deep crystallized melt pocket. A lens of anomalously dense, volatile, poor refractory mantle rock sitting hundreds of kilometers beneath the far side surface, its presence detectable only through the subtle gravitational tug it exerts on a spacecraft passing 9,000 kilometers overhead. Nothing about this can be confirmed with a single data point from a flyby trajectory. The confirmation will require a dedicated far-side geophysical lander, something with a seismometer sensitive enough to image the deep interior, a heat flow probe capable of measuring the thermal gradient through the crust, and a gravimeter with sufficient sensitivity to detect the subsurface density variations directly. NASA's planetary science community has been advocating for precisely such a mission, called Far-Side Explorer, for over a decade. China's lunar exploration roadmap includes far-side scientific stations as part of the International Lunar Research Station program planned for the late 2020s and early 2030s. The race to read the moon's far-side interior is not a competition between nations. It is a competition against time and ignorance. The accumulated ignorance of 4 billion years of geological secrets buried beneath a surface that nobody visited until 2019, and that only a handful of spacecraft have touched since. The moon has been above us every night of every human life ever lived. For 100,000 years of anatomically modern human existence, people looked at it, mapped it, worshipped it, navigated by it, and eventually landed on it. And still, the half that faces away from us holds questions that our best instruments, our most advanced spacecraft, and our most rigorous scientific analysis have not yet fully answered. The South Pole Aitken Basin is 4 billion years old. The potassium isotope signature in its rocks has been waiting to be read since before the first single-celled organisms appeared on Earth. The gravitational anomaly beneath it has been quietly distorting the trajectories of every spacecraft that has ever passed nearby, largely unnoticed, until an astronaut carrying Orion capsule flew close enough to measure it. The far side of the moon is not empty. It is the most information-dense geological surface accessible to human spacecraft in the inner solar system, and every gram of rock, every seismic wave, every gravitational deviation from every mission that has ever passed near it is a sentence in a document that describes not just the moon, but the conditions in which every rocky world in the solar system, including Earth, was forged. That document is still being translated. There is a specific quality of silence that belongs only to the lunar far side. Not the silence of an empty room or the silence of a forest at night, where the absence of sound is defined by the presence of an atmosphere capable of carrying it. The silence of the lunar far side is absolute in a way that has no terrestrial equivalent. No medium, no air, no substrate through which a pressure wave of any kind can propagate. A meteorite can strike the surface 1 meter away from a seismometer, and the instrument will record the ground vibration faithfully, but there is no sound. There is only the physics of solid-state wave propagation through rock, playing out in a vacuum so hard and so cold that it makes the best vacuum chambers on Earth look like dense, crowded environments by comparison. That silence has lasted 4 billion years. It predates the oceans of Earth. It predates the oldest rocks on Earth's surface. It predates the first self-replicating molecules in Earth's primordial seas. Every geological epoch in Earth's history, the Hadean, the Archean, the Proterozoic, the Phanerozoic with all its mass extinctions and evolutionary explosions, has played out in its entirety, while the far side of the moon sat in that vacuum, accumulating craters one by one, its surface chemistry recording every cosmic event that struck it, its deep interior slowly cooling toward a thermal equilibrium it has not yet quite reached. The number 4 billion is difficult for the human brain to process at any emotionally meaningful level. The entire recorded history of human civilization, from the first writing systems in Mesopotamia approximately 5,000 years ago to this moment, represents 1/800,000th of the age of the South Pole Aitken Basin. If you compress the moon's geological history into a single calendar year, with the formation of the moon on January 1st, the South Pole Aitken impact would occur on January 5th. The late heavy bombardment would end around January 22nd. The last volcanic eruptions on the near side would occur sometime in early March. and the entirety of human civilization, every empire, every war, every scientific revolution, every spacecraft ever launched, would occupy the final 0.2 of a second before midnight on December 31st. We are extraordinarily new here, and the moon has been watching since before there was anyone to watch. What the accumulated science of the past 6 decades has built, from Luna 3's blurry photographs to Grail's gravitational maps, from Apollo's seismometers to Chang'e 6's isotope analyses, from the Lunar Reconnaissance Orbiter's billion-pixel surface maps to Artemis 2's gravitational flyby data, is not a complete picture of the moon. It is a high-resolution outline of the shape of our ignorance. Science does not progress by filling in what is known. It progresses by making the boundary between the known and the unknown visible with increasing precision. Every mission to the moon has not answered the fundamental questions about its formation and interior. It has sharpened those questions until they are specific enough to be answerable by the next mission. The hemispheric dichotomy is real. The crustal asymmetry is measured. The creep enrichment on the near side is chemically confirmed in hundreds of rock samples. The volatile depletion signature in the South Pole Aitken Basin is now physically measured in returned samples. The gravitational anomaly in the far side deep interior is present in the Artemis 2 radio science data at statistically significant levels. None of these facts individually tells the complete story. Together, they form a coherent, mutually reinforcing body of evidence that points toward a moon whose formation and early history were far more violent, far more asymmetric, and far more consequential for the subsequent development of the inner solar system than the simple textbook picture of a moon born from a single giant impact and then slowly cooling has ever captured. The moon-forming giant impact, the collision between Proto-Earth and Theia approximately 4.5 billion years ago, is itself one of the most consequential events in the history of the solar system. The energy deposited in that collision was staggering. The combined system was partially vaporized. A disk of rock vapor and molten debris spread around the proto-Earth, and within perhaps a century, an eye blink in geological time, that disk coalesced into the moon. The moon that emerged from that process was not the cold, quiet world it appears today. It was incandescent, a magma ocean covering the entire surface, glowing at temperatures of several thousand degrees, radiating energy into space as it cooled. The light from that cooling moon would have been visible from anywhere in the inner solar system. From the surface of Mars, 492 million kilometers away at typical opposition distances, a hypothetical observer with naked eye vision would have seen a new star appear near Earth, brilliantly bright, fading slowly over millions of years as the magma ocean solidified. Not a metaphor. A physical reality, following directly from the Stefan Boltzmann law of thermal radiation, which states that the power emitted by a radiating body is proportional to the fourth power of its surface temperature. A moon-sized body at 3,000 degrees Kelvin radiates energy at a rate approximately 600 times greater than the present moon reflects sunlight. It was luminous. It was a new light in the solar system, and it burned for millions of years before fading into the cold, pale, crater-pocked object that rose over the savanna where our earliest ancestors learned to walk upright. The moon's gravitational influence on Earth has been anything but passive since then. The tidal forces the moon exerts on Earth's oceans, the same class of tidal interaction that locked the moon's rotation to its orbit, have been slowing Earth's rotation since the moon formed. 4 billion years ago, Earth's day was approximately 6 hours long. The angular momentum bled from Earth's rotation has been transferred to the moon's orbit, pushing the moon slowly outward at 3.8 centimeters per year. In the deep past, when the moon was much closer, the tides it raised on Earth were not the gentle meter-scale oscillations of today's oceans. They were walls of water tens of meters high, sloshing around the planet twice per day, their energy dissipating as heat in the seafloor sediments and coastal margins. That tidal dissipation, the grinding of water against rock, has been a measurable heat source for Earth's crust throughout geological time. The moon also stabilizes Earth's axial tilt. Earth currently orbits the sun at a tilt of 23.4 degrees relative to its orbital plane, and that tilt varies only between 22 and 24.5 degrees over a 41,000-year cycle, a remarkably narrow range. Mars, which lacks a large stabilizing moon, has its axial tilt varying between roughly 15 and 35 degrees over millions of years, driving dramatic swings in its climate that have repeatedly glaciated and deglaciated its polar regions, and may have periodically driven any Martian surface water between liquid and frozen states. Earth's narrow axial tilt variation, enforced by the Moon's gravitational gyroscopic stabilization, has kept the planet's climate within a range compatible with the continuous presence of liquid water at the surface for at least 3.5 billion years. Whether that stability was a prerequisite for the development of complex life on Earth is a question that sits at the intersection of planetary science, atmospheric science, and astrobiology, and it does not yet have a definitive answer. But the correlation between the Moon's stabilizing influence and the persistence of conditions favorable for life on Earth is not coincidental. It follows directly from the mathematics of rotational dynamics. The Moon is not a passive decoration in Earth's sky. It is an active participant in Earth's geological and biological history, a gravitational partner that has been shaping the conditions for life on this planet since before life existed, and half of it has been facing away from us the entire time. The far side carries within it the most ancient, least disturbed, most information-rich geological record of the early solar system that is physically accessible to spacecraft launched from Earth. It is closer than Mars by a factor of 1,000. It requires no life support for surface operations beyond what the near-side Apollo program already demonstrated. Its rocks have been waiting, undisturbed, for 4 billion years. The South Pole Aitken Basin is not merely the largest impact structure in the inner solar system. It is a 4 billion-year-old geological time capsule, sealed shut by the vacuum and the cold, its contents including the mantle chemistry of the early Moon, the volatile inventory of the early solar system, and the isotopic signatures of a cosmic impact event so energetic that its chemical fingerprints are still measurable today in the crystal structures of rocks that a Chinese spacecraft drilled from the surface and carried back to Earth in a capsule the size of a small car. The Artemis II gravitational anomaly will be followed by more data, more missions, more instruments, more samples. The far side story is not ending. It is reaching the point where the questions are precise enough and the instruments capable enough that the answers are within reach, not in centuries but in decades, perhaps in years. The International Lunar Research Station, the Farside Explorer mission concepts, the seismic networks being planned by both NASA and the China National Space Administration, the follow-on sample return missions targeting different geological units within the South Pole Aitken Basin, all of these are aimed at the same fundamental target, the deep interior of a world that has been overhead every night of every human life ever lived, and that is still, after all of this, not fully known. Somewhere beneath the gray, silent surface of the lunar far side, 4 billion years of solar system history is preserved in rock. The potassium isotopes in a gram of basalt carry the thermal record of a planetary scale impact. The olivine crystals in a mantle xenolith carry the water content of the deep interior. The gravitational field carries the density structure of layers that no drill has ever reached and no human hand has ever touched. The Moon rose tonight as it has every night for as long as Earth has had nights. The near side faced us, as it always has. The far side faced the open galaxy, as it always has. And somewhere in the data streams flowing from the Deep Space Network's antenna dishes into the computers of planetary scientists around the world, the far side is finally, slowly, imperfectly, incompletely, beginning to speak. We are only just learning to listen.